All right, so I've got three expressions up there, three equations up there, two of which are accurate. The last one is false. Okay? Because of what we refer to as our order of operations. When you have an exponent goes directly to the object that is in front of the exponent, right? Okay. Maybe we've seen that or understand that the best when we have, like on our calculator, we want -1 squared. We want -1 times -1. And we type it in this way on our calculator. What's our calculator say back to us? -1, right? Our calculator is doing this, taking this negative, which should be there, and now it's saying you want your 1 squared. So you want 1 times 1 like that, right? Okay. So that's what the calculator is doing, and that evaluates obviously the -1. What we really want it to do is this. We need to put parentheses around the object that we want squared when it's more than one thing, right? Okay, so we got the sign and the numerical value of 1 both being squared. So a negative times a negative is a positive, and 1 times 1 is 1. Okay, so that's where we get the positive 1. So it's the same idea when we look at these things up here. Okay, I guess I should probably maybe start with this one here, this last one. That is a inaccurate identity, because what we're saying there is that what should be getting squared there? The way we've written it, theta is getting squared, right? Okay. So the argument that we maybe kind of talked about on Friday is that if I have, let's say, sine of 30 plus cosine of 30 is equal to 1. The only time that is equal to 1 is if I square the entire sine of 30, right? And I square the entire cosine of 30. That's the only time that's going to equal 1. Right? If I maybe misinterpret or miswrite it and say sine of 30 squared like this plus cosine of 30 squared like that, what that is actually asking us to do is find the sine of 900 plus the cosine of 900. Does that make sense? Instead of taking the sine of 30, which is 1/2, and squaring that, and then taking the cosine of 30, which is radical 3/2, and squaring that. Okay. So if I do it here, like I said, I get 1/2 squared there plus radical 3/2 squared there. Obviously, fraction, so square top, square bottom. So that gives me 1/4 plus 3/4, right? And that does give me 1. So this situation is accurate. But if I do that here, do I get 1 is sine of 900, take your calculators out, plus cosine of 900. If I add those together, do I get the 1 that I'm looking for? Make sure you're in the right mode. Sine 900 plus cosine 900. I don't get the 1 I'm looking for, right? Okay. So we hopefully understand or realize here that when we write this notation, okay, we write that notation here, right there. We are not saying that sine is getting squared. We're saying that theta is getting squared, and that's not what we're looking for. Now we can fix it a little bit. Maybe we do it this way. Okay, right? Maybe those two things like that. I still look at that and say theta is the thing getting squared. Does that make sense? Okay. Now sometimes technologies, TI-83, 84, GeoGebra, Desmos, other online calculators might know what you're trying to do there. Okay. But the best thing to do is to do that. Because now order of operations says evaluate sine of theta, right? Get that back, whatever that might be, and now square to that value. Does that make sense to everybody? Okay. So that last one gets us in trouble. Okay, write it that way. So I want to make sure we talk about that. Never write it that way, because of how you or the person reading your work might interpret it. Okay. This is the real thing that we want to do. We want to evaluate sine at some angle and then square that. Evaluate cosine at some angle theta and then square that. And when we add those together, we should get 1 back. Okay. Now, in regards to kind of typeset and things in a textbook and all that kind of stuff, how it's written, And if you think about it on like your calculator, when you hit the sign button, doesn't your calculator open a parenthesis for you? Yeah. So there might actually be, it gets a little bit messier. You're probably going to actually see it written that way by hand with those extra set of parentheses around theta, okay, which I think is a good thing to have. But it starts getting messy that way, right? And so you think about typing this in on a computer or something like that for to print a textbook, you can see that can kind of get congested, okay, and it looks ugly. So to eliminate any ambiguity on where that 2 needs to go, where that power of 2, what it's squaring, we've, as a math community, developed this notation. So we put the squaring behind the function, the ratio. Okay, so now it's sine squared theta. And what I need you to understand is that these two things mean the exact same thing. Okay? The one on the left is the one that you're going to see in textbooks. You're going to see it in homework questions. You're going to see me write it that way. Hopefully you develop that writing. But the one in the middle, and especially the blue one, that's kind of the way you would have to type it in on your calculator. All right. Now, like I said, sometimes the calculator, we were messing around last period with it, and it does look like it knows what, if you leave the outermost parentheses in that blue phrase out, it looks like your calculator is knowing what you wanted to type in. And I don't know if it's accurate or not in the way it's deciphering that. My thought is, if there's question, I'm going to err on the caution side, right? So putting in one set of extra parentheses or 2 sets of extra parentheses, and knowing that that's going to be correct, that's the route I'm going to take, right? It's not really hard to add in, to know and to be confirmed that I've got the right input values. Okay, so here, this is kind of what I'm getting at here. If I've got to type this on my calculator, and I don't care what theta is, let's say I go sine of 2 degrees, and then we'll square that, plus then cosine of 2 degrees, and we'll square that. Okay, so that's kind of the way that you would want to type these in on your calculator. Okay, now like I said, your calculator may know what to do without these, but I like having, my mouse isn't really wanting to work. I like having that parenthesis and that parenthesis there, just to make sure that the calculator does what it's supposed to do. Does that make sense? Just so I know that my calculator evaluates sine of 2 first, stores that number, and then squares that number. When I hit enter, I should get 1 back. Okay. Now that 2 in there that I put in as the angle can be anything it wants to be. Okay. If I put 0.12 and then come over here, it's got to be the same argument everywhere. So I got to change this to 0.12. But I should still get 1 back. And that's an identity. It says, regardless of what that theta is, the 2 or the 0.12, you can make it, last class we made it 2,888. And every single time it gives me 1 back. Is that all right? And that's kind of what you want to do. Develop. If you ever get stuck with an identity or trying to jog your memory, is this a true identity? Okay? Grab your calculator and type it in on your calculator. See that with typing in the left-hand side, and which is what we just did, typing the left-hand side of that equation, do I get the exact same value when I type in the right-hand side, right? Now, obviously, it's a little trivial typing in the right-hand side. It's just 1. But we'll see some examples here today where the right-hand side is another trig expression. We type it in, do we get the same answer back? And that should maybe shed light on the fact that you do have an identity. Okay? We're going to have a lot of identities in this class, a lot of statements that are always true based off of what you choose as an angle. And there will be times where you mess them up, okay? Because a lot of them are very similar. Okay? My hopes are that you don't try to memorize things. Because today we might see, upwards of 15 different identities. And
Really easy, and they're all very similar looking. Really easy to mess up a plus sign or a minus sign. Really hard, or easy, I guess, to mess up. Which trig ratio is, I always mess up secant squared and cosecant squared. I flip-flop them in their identities that they exist in. It's really easy to do. So my hope is that we develop associations, we develop maybe an understanding of how they are created, and that will help us learn these things so we don't mess them up. Does that kind of make sense? And really, right now, the one that you need to know the most is sine squared theta plus cosine squared theta equals 1, because that's going to get you all the other ones that you need. So if I go sine squared theta plus cosine squared theta is equal to 1, we talked about on Friday that I can subtract something from both sides, right? Well, let's just isolate the cosine. I get cosine squared theta is equal to 1 minus sine squared theta, right? Hopefully you see the fact that you should never memorize this. Don't memorize that, because was it really easy to develop from that? So that's my argument with all of these. They're really easy to develop, so don't memorize them. Just know that they exist, and through a little bit of simple algebra, you can create them. So sine squared theta is equal to 1 minus cosine squared theta. Okay? Some others that exist from that. Can I square root the left-hand side here? Can I square root the right-hand side there? So now we would get cosine of theta is equal to square root of 1 minus sine squared theta. Well, when I take the square root of something, I get plus or minus, right? So now through the use of that one, if I ever have to use that red one, I have to know what quadrant theta is in, so I choose the right plus or minus sign. Okay? Because here it says cosine of theta. Well, what if theta is in the second quadrant? That number should be negative, right? Cosine's in the third quadrant, that should be negative. In the first and fourth quadrant, we should choose the plus sign. Plus 3. And I can do the same thing for the sine then. So sine of theta is plus or minus 1 minus cosine squared theta. Okay? So there are 5 total identities there, right? But they're all developed, they're all conclusions that fall from just knowing sine squared theta plus cosine squared theta equals 1 and a little bit of basic algebra, right? Okay? So show you that sine squared theta plus cosine squared theta equals 1 is one of your 3, what we refer to as Pythagorean identities. Okay? Your next Pythagorean identity is taking that initial one and just dividing through by one of the 2 ratios that are in there. Okay? So let's just look at sine squared. I'm going to divide every single thing up there by sine squared. So what's sine squared divided by sine squared? 1, right? Divide that by sine squared. I'm going to divide this by sine squared. So what's cosine divided by sine? And maybe this would help you. We know tangent is sine divided by cosine, right? So if I do cosine divided by sine, it's the flip of this, right? It's the reciprocal of that. So what's the reciprocal tangent? Cotangent, okay? So I divide that by sine squared, I get cotangent. So 1 plus cotangent squared theta should equal. Now, if I divide that by sine squared, what's 1 divided by sine? Cosecant. So I got 1 divided by sine squared, so it should be cosecant squared, right? Does that kind of make sense? That's just dividing everything through by sine squared and evaluating those those trig ratios. Now from that, just think here, can I get the square root of both sides to get cosecant theta? So that would give me a plus or minus version of that. I could maybe subtract 1 from both sides, right? I could subtract cotangent squared from both sides to get another identity. And then I could actually subtract this 1 from both sides and then take the square root of both sides and get what cotangent theta is equal to. So there's another list of 4 or 5 additional identities that come directly from that one, just by adding or subtracting from both sides and then square rooting both sides. Does that make sense? I'm not going to write those down, but I think if you ever need them, that's how you would approach them and develop them. The final Pythagorean identity that we come across is taking this and divided by sine already, right? What's my other option? Divide by cosine. So what's sine? If I divide this by cosine squared, what's sine squared divided by cosine squared? Tan squared. cosine squared divided by cosine squared is 1. And then 1 divided by cosine squared is secant squared. And that's your third identity. Now, this is what I said earlier, is that I mess up the secant and the cosecants and which ones they go in. Okay? Because my memory is going to fail me at some point. I'm going to transpose things. I'm going to mess up pluses and minuses, all that kind of stuff. So I don't try to force myself to memorize it. If I ever recognize that I need them in a problem, I do side. I just do a little chicken scratching on the side of my paper, and I come up with those, and then I apply them. Okay? I think that's the safest thing for you to do as well, so that you don't make mistakes in the signs or the specific ratios that should be in those things. And then I got one. There's 4 or 5 that are identities that fall directly from it. Right? Like just using subtraction, taking squares. So those are your 3 what we call Pythagorean identities. Okay. So that might be, if we write them all out, that might be a cluster of like, I don't know, 12 to 15 identities. But what did they all stem from? They all stem from one identity, right? Okay. One identity, doing a little bit of division, then doing a little bit of subtraction and square roots, some algebra that we are all capable of doing. Okay. And that develops all those other ones, right? Okay. If I'm ever in a situation and I don't know, is this an identity? Maybe I'm on a test and I have tried to memorize things, but I messed things up. And I want to know, is that an identity? Should I take my calculator and type this in, choose a theta, hit enter, and then type this in, choose the exact same theta, and hit enter? If they give me back the exact same number, is it an identity? Yes. Okay. Now, I would be cautious with just doing that once with some arbitrary theta, because it might be a coincidence that you have solved that equation for the one time that condition exists for it to be true. So rewrite it with maybe theta being, maybe you chose 31st. Maybe then you want to check, okay, well, is it the same with 33 degrees? It's the same with 42 degrees. Check it a couple times and make sure that you get that equation to be true. Does that make sense? So you can use your calculator a lot in this course. If you understand how it works, you can use it a lot in this course to kind of jog your memory of particular identities. Okay? So that being said, in that little short introduction I did, and we're going to use these things a lot, so the sooner you learn them, the better. But I'm not saying you're going to be an expert at this stuff. At the conclusion of today, we're going to go and use this stuff a lot for the next 8, 9, 10 weeks. Okay? That should allow us to maybe get to these last 3 or 4 questions from the notes, and that will then help you get to those last 4 or 5 questions in your homework. One of the common questions throughout the entire textbook, the entire year, is to take one trig ratio and write it in terms of another one. Okay? And that's all they're saying. They say express sine of theta in terms of cosine of theta. Sometimes this is easy. Sometimes it's really, 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 really hard. Sometimes you use one substitution. Sometimes you might use 5, 6, 7 substitutions. It's just a matter of what you're supposed to start with and what you finish with. Okay? This task is going to be played out all semester long. So again, the sooner we kind of grasp it, the better the rest of the course is going to be for us. But when I'm going to say, if I were to say take like 2x plus 4y is equal to 12, I could take that equation and say express y in terms of x. And what does that mean for you to do? Express y in terms of x. Does it mean this? I just express y in terms of x. Yeah. I've solved for y. That's basically what it means, express y. Write what y is equal to. In terms of x means x is the only thing on the other side of the equation that kind of dictates what y is, right? Okay. So, same idea here. We want to be able to express sine in terms of cosine. So I need an equation that relates those two things. An equation that relates sine and cosine. Does that relate sine and cosine? When I mean relate, that it has both those things in it, right? And we could adjust it a little bit
so that I've expressed sine in terms of cosine. And I take sine and isolate it. And basically, when I see that, it means I'm going to solve for sine. Okay, I'm going to sine theta all by itself. So this is sine squared theta right now, minus 1 minus cosine squared theta. And then I would take square root of both sides, right? So now I'm taking square root of both sides. I guess something like that, right? If I solve for sine, am I expressing sine? I'm telling everybody what sine is in terms of cosine. Okay? The idea here, and this is always something every year that people struggle with, what that phrase "in terms of" something means. Okay? It means on the other side of the equation, that is the only thing that they want to be left over. Now there might be pluses and minuses and other mathematical operations over there, but the only trig ratio that's on that side can be cosine. If I would have done something to where maybe I get cosine and tangent on that side, that's a problem. Because it's not in terms of just cosine, right? It's in terms of cosine and tangent. So I have to do some work to kind of alleviate that. You see it maybe best in this example B here. It's express tangent in terms of sine. Okay? So I'm going to work through and try to figure out what ratios or what identities do I know incorporate tangent and sine. If we come back up here, doesn't this one right here incorporate tangent and sine? All right. So what happens, guys, is that when you're asked to do these questions, you're only going to be really successful if you didn't know tangent theta is equal to sine or cosine. There's no way you're going to be able to do example B here, right? Does that make sense? So it's paramount that we understand and we learn these relationships so that we can apply them later on. So I'm going to start off writing that. Get it up there in my tablets. I'm going to start off writing that tangent of theta. Tangent of theta is equal to sine of theta over cosine theta. So right now I've expressed tangent in terms of sine and cosine, right? I want it just to be in terms of sine. So I need to get rid of the cosine, right? Okay. Well, I need to get rid of the cosine, and chances are when I do that, I'm going to probably bring in another ratio. I'm probably going to hopefully try to bring in sine again, right? So this is where we've got to do a little bit of maybe side work and understanding that what I want to be left with on the right-hand side is just the word sine. Now, it can show up 2 times, 3 times, 4 times, 1 time, whatever. But I want only sine to show up. So then I'm going to go to the side and say, okay, well, I know this. I know that relationship exists. Can I solve that for cosine? I do this. Cosine squared theta is equal to 1 minus sine squared theta. And then cosine theta is equal to 1 square root of 1 minus sine squared theta, plus or minus. Do we know that that's true? Yeah, that's an identity, right? We work through those identities. So now, again, this is an identity. And identity is basically, right now, the way we're going to view them is just tools for substitution. Okay? They are valid substitutions that you can make anytime you want to. So instead of seeing this cosine here, can I rewrite that cosine as this plus or minus 1 minus sine squared theta? All right, so I'm going to rewrite this tangent theta as sine theta divided by, plus, I'm going to put plus or minus here, we'll talk about that in a minute. But now cosine theta is plus or minus 1 minus sine squared theta. Now, have I expressed tangent in terms of sine? Sine, the only ratio that you see here. So if I wanted to know what tangent theta was, and I didn't know cosine theta, I didn't want to go through the work to find cosine, but I knew sine. Maybe in the problem they tell me sine of theta is 1/2, and they want me to find tangent theta. I could use this formula now instead of having to do the work to find what cosine is. Does that make sense? So there is and we'll see examples of that. That doesn't make sense right now. We'll see examples of that in the next couple of weeks. But we've got an issue here because that is actually 2 answers, right? That's a plus and a minus. Okay. That's where this comes into play. You got to pay attention to that kind of stuff. They tell you that for a reason. It's not something to glaze over and just say, oh, it's just kind of routine that they always give you that. It says quadrant 2. Theta is in quadrant 2. Okay? Cosine in quadrant 2 is what kind of number? negative, right? Okay. All students take calculus, so cosine is negative here in quadrant 2. So which one of these versions do I take? I take the negative. Okay, so for that, tangent theta then is equal to negative. And now the reason I had to do that is because tangent in the second quadrant is what kind of number? Tangent's negative, right? In the second quadrant. And right now, we have a positive divided by a negative, right? And that should tell me that tangent should be evaluated as a negative number. So what this means to us, guys, is I'll take my calculator out. And I'll take and type in tangent of, say, any degree you want to. And then hit it. It gives you a number back, right? Type in this ratio with the exact same theta. You should get the exact same decimal now. Okay? And it should have the right sign with it, SIGN. Does that make sense? And that's actually, guys, that's another identity. All right? But probably one that is so rare that we don't need to memorize it. Does that make sense? And we're not going to use it a lot. If I need that identity at any time, we'll go through it and we'll develop it. Okay? I'm going to, because we're running out of time, obviously, but you're going to need to know these two examples to finish your homework. So here during third period, I'm just going to sit down. These are really easy, actually, once you draw a picture. So I'm going to put those together, and you guys just watch those on your own. It'll be maybe 5 minutes, and then you should be able to finish up that assignment. Okay. There's a formula down here for areas of triangles. You guys know 1/2 base times height, right? But there are a lot of other formulas for areas of triangles. That's one of them. I'm not really concerned about that right now, but it is in this section. But I didn't give you any homework questions over that, so don't worry about it. If we need that, we'll come back and talk about that area. Probably even talk about that when we start talking about law of sines and law of cosines, because that's really the reason that formula exists. Okay, so these questions here, they're essentially giving you the necessities to create a right triangle in the coordinate plane, but they're, with your right triangle, you could have, you got your opposite side, your adjacent side, and your hypotenuse to some angle. So as long as you know two of those sides, you should be able to develop the third one. That's what they're kind of doing here, but kind of hiding the fact that, here's your opposite side, or here's the hypotenuse. They're hiding that information inside the ratio, in this case, of tangent. So I'm just going to draw a real quick picture here first. We're in the coordinate plane. They say theta is an angle that terminates in quadrant 3. So I want to draw out some angle in quadrant 3. It doesn't really matter how big it is, as long as it terminates over here. Okay, so that's my theta. And we know we've been working with, dealing with that terminal ray and then dropping that right angle there, creating that right angle with the x-axis. And when we've talked that is, your theta bar, okay, that angle to get back up there. But once we've developed this triangle, we actually have enough information here to find the cosine that they provide us, or that they're asking for. If you're dealing with tangent of theta, and theta is this angle, it resides in the third quadrant. Tangent, remember, is opposite over adjacent. Okay, so if I'm looking at this being theta bar, opposite, so theta bar and theta are going to tell me the same information. Tangent theta is opposite over adjacent, so 2 over 3. So I'm going to go opposite this theta bar, and that gives me 2. And I'm going to go adjacent to theta bar, and that gives me 3. Now I'm also going to, once I know those two values, it's a right triangle, a squared plus b squared equals c squared, so the Pythagorean theorem. If I square that, I get 4. Square that, I get 9. Add them together, I get 13. So this distance here is a square root of 13. So right now we have all the components we need. And this is a, sometimes we overlook this, but using this theta bar is actually telling you that, if I come back up into this quadrant here and draw this triangle,
with theta bar right there. This should be 2, this should be 3, and this should be radical 13. It's the hypotenuse. I never do that. I'm not saying that you can't, but I just deal with this triangle down here because it's going to give me the same information. But when I look at this triangle here, and I want to talk about this 3, I want to talk about that 2, if I started at 0, 0, and I try to get to this point right there, I have to travel 3 units to the left. So that should actually be a negative 3. And then I got to travel 2 units down. So that should be a negative 2. So now I should be able to say, okay, if this is cosine of theta is what they're looking for, cosine of theta, well, cosine is adjacent divided by hypotenuse. This number is my adjacent, and radical 13 is my hypotenuse. If I rationalize that, I get that number there. Okay, that's the exact same thing. Like if we were to, put this theta bar, reference it back to the first quadrant, and say that this is 3, and this is 2, and this is root 13. The cosine of theta bar here would be 3 over root 13, which evaluates to 3 root 13 over 13. Okay, but remember that cosine, theta is in quadrant 3, and cosine in quadrant 3 should be negative. Okay, so there you do kind of two different approaches or two different perspectives. You get the same answer. So they could ask me, they could ask me all types of things. They could ask me the sine of theta. Well, sine of theta is, looking at this approach over here, it's the opposite divided by hypotenuse, so negative 2 over root 13. You can rationalize that, let you do that on your own. But if I did that over here, I get, the sine of this theta bar, my reference angle would be opposite over hypotenuse, so 2 over root 13 again. But remember, theta needs to be in the third quadrant, and sine in the third quadrant is a negative value. So negative 2 root 13, same idea, same result. So that's what we're doing there. This question here is the same idea. A couple different things you can think about. I'm a person that I don't like dealing with secant. I'm going to change that to cosine. So this question is written, says if secant of theta equals 2 and theta is in quadrant 4, that's exactly the same thing as saying if cosine of theta, if secant is 2, cosine and secant are reciprocals, so the cosine should be 1/2. And think about this, secant, I'll do it this way, cosine of some angle is adjacent divided by hypotenuse. Well, secant, it's reciprocal, so that should be hypotenuse divided by adjacent. So right now, we're seeing that secant is 2 over 1, so my adjacent side is 1, and my hypotenuse is 2. So if you're a person that likes to do it that way, always deal with the sine, cosine, and tangent instead of the reciprocals, go ahead and do it. I like it. We can do it both ways. But now, if secant theta is 2, that's saying the exact same thing that cosine theta is 1/2. Theta is in the fourth quadrant, so theta is going to be over here. Maybe that's the angle theta. I'm going to develop this little right triangle again. Okay. Let's put theta bar in there. And sometimes you might even see, because I don't know that theta bar is really the appropriate variable to use. Sometimes people use alpha in there. Doesn't really matter. But we're saying that the secant of this is 2, or the cosine is 1/2. Well, if I say cosine, which is adjacent divided by hypotenuse, that's the positions of the 1 and 2. Or if I would have said secant, which remember secant of theta is hypotenuse divided by adjacent, so that's 2 over 1. That just means put the 2 here first and then the 1 there, but it's still the same thing. So either way you want to view it. Now just be careful, because this is where people will get themselves in trouble. Using the Pythagorean theorem, you now know a squared, but you don't know this distance here. I'm going to call that y. You don't know y. You do know your radius squared, which would be 4. So now y squared would be 3. So this distance here is root 3. But because it's in the fourth quadrant, that value should be negative. If that's the way if you're gonna view it without redrawing the first quadrant picture. So now if they want let's say the sine of theta, this is the reason I like this picture here, because now I can go through and find the remaining trig functions real quick. It's the one I missed, cotangent. I go through and find these real quick. Sine, opposite over hypotenuse. So negative root 3 over 2. Cosine is adjacent over hypotenuse, 1/2. Cosecant, remember cosecant is a reciprocal of sine. So it's going to be negative 2 over root 3, which ends up being negative 2 root 3 over 3. Tangent is opposite over adjacent, so it becomes negative root 3. In cotangent, it's reciprocal, so negative 1 over root 3, which equates to negative root 3 over 3. And that's how we come up with in those 5 other trig ratios. What's nice about this is that we should, because of the numbers that show up here, and we haven't talked about inverse ratios yet, but if I know cosine of theta is 1/2, and I know sine is root 3 over 2, well, this is right now in the form of n, 2n, and n radical 3. So that tells me theta bar actually is a, 60-degree angle, because it's across from the n radical 3 side. So they're telling me then theta here, this theta, was actually 300 degrees. And that's something we'll kind of work on later as well. But another way of doing this is to say, like I just kind of going up through using the reference angles. If we know it's in the 3rd quadrant, and the secant is 2, so it gives us that theta bar angle right here. Maybe I put that theta bar up in the 1st quadrant, and opposite that we had root 3. This would have been 1, and that would have been 2. So we can get the sine of theta, cosine of theta, secant theta, cosecant. I guess we already got secant. That's providing the question. Tangent and cotangent. We can do that exact same thing, get the exact same answers using this picture instead of maybe this one. But before we go and do that, before you use this reference triangle, you would want to make sure, okay, if I'm in the 4th quadrant, the sine in the 4th quadrant is negative. The cosine in the 4th quadrant is positive. The cosecant is the reciprocal of sine, so it's got to be negative. The tangent, all students take calculus, tangent is negative in the 4th quadrant. And then cotangent's reciprocal is negative as well. So it should give you the correct negative, positive, negative, negative, and negative that we would get gotten with this picture. And then we just go, okay, well, sine of this one would be opposite over hypotenuse, so root 3 over 2, and you see that that answer is exactly the same as that one there. Cosine would be 1 over 2, and you see that that answer is exactly the same answer as that one there. And you can go through and find the other ones, and you'll get the exact same answers with the exact same signs, the SIGNs. So that's kind of what we're looking at there. In the event that we need to deal with area of triangles, just go ahead and put this on video. This is the area of A of a triangle with sides lengths of A and B and the included angle theta. Meaning that the included angle means it's the angle that's created by the two sides that you know the lengths of. So I got to know, basically, if you remember back from geometry, this is side, angle, side. That's kind of the orientation of parts, and you see that with side, angle, side, A is included. It's between the two known sides. So they're saying that the area here of this thing, area, is 1/2 the length of side A times the length of side B times in the sine of 120. So then, obviously that's, 15 times sine of 120. Now, if I was doing this wanting exact values, sine of 120, okay, so 120 is maybe that there. Theta is 120. So my reference angle then is this 60 degrees. Okay, so across from 60 is always going to be my radical 3 side. Across from 30 is always my 1 side, and this is 2. So when they say sine of 120, they're actually saying that that evaluates to opposite over hypotenuse, so root 3 over 2. So that's the same thing as sine of 120. It's in the 2nd quadrant, so it is a positive number. and then times my 15. So I would actually have 15 root 3 over 2 as the exact area of that triangle. Okay, so let's see how that exact answer kind of plays out decimal wise. If I would just take in, 0.5 times 10 times 3 times sine of 120. Make sure I'm in the right mode. I'm in degrees. Hit enter. That's what I get decimal wise. And obviously we'll have to round that. But that should be the exact same thing as 15 root 3 divided by 2. And I don't need any parentheses here. My order of operations says do that multiplication first. Evaluate that and then divide that by 2. It should give me the same 12.99 number. So that there is the exact answer. One of these I would actually have to round to a particular decimal, no longer making it exact. So that's another formula for area triangle. You guys know area is 1/2 base times height. And if you remember what height is an altitude. So in order to find the area of this triangle, I'd really need to know maybe what that distance right there is. That's the altitude, to be from a vertex perpendicular to a line containing the opposite side. That's the definition of an altitude. So I need to find that solid red line, that distance. That's really hard in this problem maybe. Or maybe I could find that's another altitude right there, if that's a right angle. Maybe I need to find that blue distance. And the remaining altitude would be, kind of looks like, if I extend that side, maybe that would be the remaining altitude. But my hopes are that you realize that each of those three distances, those three altitudes, would be, in this particular problem, really hard for us to find out. Maybe it's impossible for us to find out. I don't know. But if I want to find the area without needing those things, this is a technique that will work. Maybe when we get a little bit more trig under our belt, with law of sines, law of cosines, that kind of stuff, maybe we come back and learn why this formula is what it is. Maybe we can do the derivation of that formula.